We're going to continue our discussion on measures of spread by looking at quartiles and then as part of that percentiles. These are both ways of ranking data, so looking at the order that each observation falls in a data set. And so percentiles here are useful for comparing values in a data set. For example, you may have taken a college entrance exam like an SAT and found what percentile you scored on the test. So for example, if you scored in the 85th percentile on the math portion of the SATs, that would tell you that you did better than 85% of the people who took the math portion of the SATs that year, and that only 15%, so 100% minus 85%, only 15% did better than you. So that would be an idea of how to compare observed values. We're told that the kth percentile is the data value that has k% of the data at or below that value. So in the example we just did, the 85th percentile means that 85% of the data are below that value and the other 15% would be above. So taking a look at quartiles here, quartiles are three special locations in a data set. There is going to be the first quartile, the second quartile, which happens to be the same as the median, which was one of our measures of center, and then the third quartile. And I always have in class kind of a conversation around why there are three quartiles when the word quartile sounds like fourths. So I just want to give you a real quick visual up here at the top. If I have a data set and I'm just gonna say that's my minimum value and that's my maximum value, we said that the second quartile was the same as the median. So remember, the median was the data value that had 50% of the values below it and 50% above it. So I'm just gonna call this Q2, which equals the median. And then hopefully from looking at this, it would seem obvious then that the first quartile would go right in between the minimum and Q2. And the third quartile would go right in between the maximum and Q2. And so that's what we're saying. That's why there are three quartiles, but they divide the data set up into fourths. And so what's happening here is that we have 25% of the data ends up within each of these regions. Okay, the one I drew was nice and evenly spaced. That is certainly not always going to be the case. So sometimes the length of the line, the gap between minimum and Q1, for example, might be longer than the length of the line segment between Q1 and Q2. And we'll talk about what that would mean a little bit later, okay? So the second quartile, Q2, is going to be the value that divides the lower 50% of the data from the upper 50% of the data. This was just our median. Q1 is going to divide the lower 25% from the upper 75%. And then Q3 is going to divide the lower 75% from the upper 25%. Calculating quartiles by hand, there are several different methods of doing that. And depending on which method you use, you might get slightly different answers. So for consistency, we are going to just use the calculators. Okay, so we're going to go ahead and move into an example of calculating quartiles. So this data set you'll want to fill in. This is from one of my in-person classes, and we have here the heights of students in our class, and we're asked to find the quartiles using the calculator. It says and by hand. We're going to skip that. We're just going to do it using the calculator. So the way to find the quartiles, first thing we're going to do, just like we would pretty much anytime we're inputting a list of data, is we're going to go to Stat, hit Enter on Edit, and we're going to enter those data values. So you can do that now if you haven't already. To save us some time here, I've already entered those values. And so once you've got the data values entered, you're going to want to hit Stat, scroll over to Calculate, and choose option 1 that says 1 var stats. Now we've used this option before when we found, for example, the mean and the standard deviation. So if you hit enter, make sure you entered your data in list 1 and have list 1 highlighted there. Scroll down and hit enter. You'll notice it gives you the sample mean. Like I said, we've used this option in the calculator to find sample mean before. There's our sample standard deviation S. There's our population standard deviation sigma. But you'll notice there's this arrow, this down arrow. That means that if we push the down arrow, we will get more output. And so those are the values we're actually looking for. You'll notice we're given that Q1 is 64. Q2, which is the same thing as the median, is 68. Q3 is 70. And then you'll notice it also gives you the minimum and the maximum. The reason that those are there is, so that was that example. The reason those are there is that one of the things we're commonly going to use when we look at measuring spread is what's called the 5-number summary. And so the 5-number summary is just a comma separated list of the minimum, so the smallest value in the data set, Q1, Q2, Q3, and then the maximum. Other things that we're going to need to be able to calculate are these two. So the interquartile range, which represents the spread, so the variability of the middle 50% of the data set, and it's calculated by taking Q3 and subtracting Q1. And then being able to determine if we have any potential outliers in the data set. And so we're going to be able to calculate what's called the lower fence, or sometimes the lower limit, and then the upper fence, sometimes called the upper limit, and these are the formulas for those two. Okay. What we end up finding is that if we have a value in our data set that is smaller than the lower fence or larger than the upper fence, we consider it a potential outlier. So we're going to go back to our data set above for height, and we're going to find the interquartile range, the lower fence, the upper fence, and the 5-number summary. We're supposed to determine if there are any potential outliers as well. And so we're going to start with the 5-number summary. Which, remember, is just a comma separated list of your smallest value, Q1, Q2, Q3, and your max. So our smallest height was 59 inches, so 4'11". Our Q1 was 64 inches, Q2 was 68, Q3 was 70, and our max was 80. So we had a student who was 6 feet 8 inches tall in that class. So there's our 5-number summary. Once we have that, we can calculate the interquartile range, which we abbreviate IQR. That is found by taking the difference between Q3 and Q1. Q3 was 70, Q1 was 64, and so we get 6 inches as the difference between 64 and 70, and so that is our spread of the middle 50% of the data. So we're saying there's about a 6-inch spread between the middle half of heights of students in our class. What we're going to look for now is determine if there are any potential outliers. And to do that, we need to find the lower fence, which I'm going to abbreviate LF. The lower fence is the first quartile minus 1.5 times that interquartile range. So Q1 was 64 inches, minus 1.5 times the interquartile range was 6. So we're taking 1.5 times 6 and then subtracting that from 64. And we get 55 inches. So what that tells us is if we have any student in our class who was shorter than 55 inches, that student's height would be a potential outlier. Remember, our minimum height was 59 inches, so we don't have any potential outliers on the short side. Our upper fence is, the formula for that is Q3 plus 1.5 times the interquartile range. So we looked the same distance, right? 1.5 times the interquartile range, either below Q1 or above Q3 is the process. So Q3 is 70 inches. And so we are looking at 70 plus 1.5 times 6, which would be 79 inches. And so what we're saying there is any height above 79 inches is going to be considered a potential outlier. And we did have one of those. If we look back at our data set, we had a student that was 80 inches tall. And so what this tells us is that the height of 80 inches is a potential outlier. Okay, and the reason we call it potential, by the way, is because this was just from a sample of students. If we had included more students, that height might not have looked so unusual, right? So it's saying based on this particular data set, that one looks like it's potentially unusual. Okay. The last thing that we're going to do then is we're going to move on to talking about what are called box plots. And in a box plot, we're going to get a way to visually see the spread in the data that we looked at using the 5-number summary. So when we calculated this 5-number summary, we just have this list of 5 values, and sometimes it's a little hard to visualize spread when you just have a list of numbers. And so we're going to learn how to do that visually. Anytime that you have a potential outlier, at least one or more, you're going to do what we call a modified box plot, where you individually plot potential outliers. So I'm going to do both for you. I'm going to do what a regular box plot would look like and then what a modified box plot would look like. So it says here, important, you must use a scaled number line when drawing a box plot. So at the beginning here, when I was showing you what box plots looked like, I drew this sketch and I had min, Q1, Q2, Q3, max, and they were all nice, evenly spaced. And it's really tempting for students to just draw a box plot that always looks like that and then label numbers at the bottom. But remember that scaling is important in mathematics. If we're going to try and get an idea visually of what something looks like, we need a numerical scale. And so I'm going to do just a regular box plot first, and then I'm going to do a modified box plot below. Like I said, in general, if you have outliers, you should be doing a modified box plot. Okay, but I want you to see what a regular box plot would look like for a data set where you had no outliers by just pretending that this didn't have an outlier. So these, remember, we're representing height. So regular box plot first. I'll just leave it there. So height, our smallest value was 59 inches. So I'm going to start here at, let's say, 55, 60, 65, 70, 75, and 80. Once you've got your axis labeled and you'll notice we used a nice consistent scale. So each time we went up by 5, we used the same amount of space to represent those 5 units. What you're going to do next is you are going to graph what looks like a 2-segmented box using your values of Q1, Q2, and Q3. So if we go back to the 5-number summary let me slide this down a little bit. For our height data, we had Q1 was 64, Q2 was 68, and Q3 was 70. So those 3 values are what you're going to form your box from. So 64 is right about here. That's Q1. 68 is right about here. And 70 is right about here. And so again, that's what you're going to use, those 3 values, Q1, Q2, and Q3, to form your box portion. And then you're going to, in general, if you didn't have any outliers, you would just extend what we call the whiskers down to the minimum and up to the maximum. So the minimum was 59, that's right about here. The maximum was 80, and that's right about here. And that's what a regular box plot would look like for this data set. Remember what we said right earlier, where we said that each segment there, so between the minimum and Q1, that represents 25% of your heights. Between Q1 and Q2, that represents another 25%. Between Q2 and Q3, there's another 25%. And then between Q3 and the max is another 25%. So what we're seeing here is that there's a big cluster of students, heights here, that are right around between 68 and 70. So that's between about 5'8" and 5'10". There's 25% of the data there, but the spread's only 2 inches. So there's just a whole bunch of students clustered there. Whereas once we get much higher than that, there's a 10-inch spread in the next 25%. Okay, so you can see kind of a cluster of values here, a few sprinkled down here, and then a few sprinkled up there. As far as the modified box plot goes, so this is what we should really be doing for this data set because we did have a potential outlier. We're going to use the same scale because it's the same data set. These are still representing height in inches. Initially, this is going to look exactly the same. So we're still drawing our box using the 3 quartiles, 64, 68, and 70. So that hasn't changed at all. And then what we would do, here's where the change comes in. In a modified box plot, we're only going to extend those whiskers to the largest and smallest values in our data set that are not potential outliers. So the smallest value in our data set is 59. 59 was not a potential outlier, and so we would go ahead on the low side and go all the way down to 59. So there is no difference on the low side of what either of these box plot versus modified looks like. On the upper side though, we're going to extend that top whisker to the largest value in our data set that is not a potential outlier. So as a reminder, 80 here was a potential outlier. So we would extend that whisker to the largest value that's not a potential outlier. That's 73. So the change here is that this whisker only comes up to 73. And then we plot any potential outliers individually with an asterisk. And so what that really is telling you is, whereas this one you kind of get lost in, yes, I can see there's a lot of spread here. While we make it a modified box plot, you can really see that really there's not a whole bunch of spread on this upper side. You just have this one outlier that kind of made it appear that way. Okay. And so one of the common uses of box plots is to look for differences between two or more different groups of populations. And so sometimes you're going to see box plots that are like stacked one on top of the other, so that you can visually compare between one population of interest and another. Okay, so those are examples of box plots. Really quickly, I want to show you how to do this in the calculator, and then we'll be wrapping this one up. Ordinarily, we would go to Edit, so Stat, Edit. We would enter our data set. Our data is already listed in List 1. We would then go to Second and Stat Plot. So Stat Plot is a second function on y equals. Hit Enter there on Plot 1. And if your plot is currently set to off, you're going to scroll to the left arrow so that it says on, and hit Enter so that on is now bolded. And then you're going to scroll down to Type, and you can see there's two different types here. So there's the modified box plot. You can tell the individual dots. And then over here, this is the regular box plot without the individual dots for the potential outliers. So we're going to go ahead and we could do either one or both. We're going to go ahead and do the modified box plot. Once you've hit Enter on that plot to show we're doing a modified box plot, we entered our data in List 1. Here's the thing people always forget is you can't just hit Graph. If you just hit Graph, you're not going to see anything. You have to hit Zoom and scroll down to Zoom 9. And this is telling it we want you to look at the stat plot when you're graphing. Then you can hit Enter and you'll get the modified box plot. Okay, so that's the modified box plot for this data set that we just did. If you hit the trace key, so right here, hit trace, you'll notice it tells you, oh, the minimum was 59, and we knew that, right? If we hit the arrow keys, we can trace along this. It tells you Q1 is 64. So it's telling you right along the bottom. It tells you that Q2, the median was 68. It tells you that Q3 was 70. It tells you the largest value that wasn't a potential outlier was 73. And then it tells you you had an outlier out there at 80. Okay, so that's a nice, quick, easy way to look at the graphs as well. So we can do box plots by hand or on the calculator.